A lot of people online today, so. And so for right now, the 3-3 through 3-7, those homeworks are all due Friday. And if we don't get through all 3-7, that'll be moved back till next week. Okay. So the last time we were dividing polynomials, and I just want to remind you, again, this is still 3-5. So I want to remind you of how synthetic division works, all right? So when we're taking, and I've been doing cubic, so let me go quartic, x to the fourth minus 5x to the third plus 3x squared minus x plus 7. And I want to divide all of that by x minus 3. What I'm going to do, remember, synthetic division only works when we have x minus a number in the denominator. So this is only for this type of division. And if we have that, we write the 3, and then we write the coefficients in descending order. Of my dividend there. So 1, -5, 3, -1, 7. By the way, I've always started with 1s out front here. You don't have to start with 1s out front as the coefficient of your dividend. You can start with whatever. Doesn't matter. And the process of synthetic division is the first step is to bring down whatever this coefficient is. In this case, that's a 1. Then I take, and every time I see a number down here, I multiply it by 3 and put it in to that spot. So 1 times 3 is 3. Now I put it in over here. Then I add. That'll give me -2. Once again, I multiply by 3. -2 times 3 is -6. And then I add. That's a -3. Then I multiply by 3 again. 3 times -3 is -9. I add those. That gives me a -10. And then lastly, 3 times -10 gives me a -30. When I add those, I end up with -23. Now on top, this represented the coefficients. No, that was x to the fourth. Shoot, dang it. Wrong one. So on top, these represented the coefficients of x to the fourth, x to the third, x squared, x, and my constant. On bottom, this represents the coefficients of 1 less. So x to the third, x squared, x, my constant, and then my remainder. And so what I'm saying is that if we take x to the fourth minus 5x to the third plus 3x squared minus x plus 7, and then divide all that by x minus 3, what we end up with is x to the third minus 2x squared minus 3x minus 10 with remainder of negative 23. All right, that's what this is saying. That's what this process is saying. So that's synthetic division. Now, here's an interesting fact that hopefully we can discover. Let's pretend my dividend, this polynomial on top, is actually a polynomial function. And then let's plug in the number 3 into that polynomial function. So if I take my calculator and I take 3 to the 4th power minus 5 times 3 to the 3rd power plus 3 times 3 squared minus 3 plus 7. What do you get when you calculate that? Interestingly enough, if you've done this right, you should get negative 23. That's strange, right? You got the same thing as the remainder up there. Okay. Think that's coincidence?
Probably not.
Probably not if I'm talking about it, right? Probably not if I'm talking about it. Let's try it from another one. Let's try one from the one we did yesterday. Now, I forgot, but I took a picture of the one that was on the board we did last class period. So I'm going to try to rewrite that. So last time we did synthetic division. It was x to the third minus 2x squared plus 1 over x plus 2. And we got x squared minus 4x plus 8. That was one of them, with remainder of negative 15, right? So again, that was just from last time. So if you look back in your notes from last time, we have that problem done via long division and synthetic division. So let's pretend we have a polynomial function And remember the r here, since it's x plus 2, the r is at -2. So let's plug in the -2 and see what we get. Sure enough, we get out a -15. So that's an interesting phenomenon. And it turns out it always has to happen that way. Okay. And the reason it always has to happen that way is a consequence of something called the remainder theorem. All right. So let's talk about the remainder theorem. Let's imagine we're going to divide a polynomial function by x minus r. The polynomial function that I'll use, I'll just write as p of x for polynomial function. That's the dividend, all right? So we're going to divide that polynomial function by x minus r, and we're going to get some other polynomial, like this piece, with a remainder. So I'm going to get q of x, called q because it's the quotient, plus, or let me rewrite this, with remainder capital R. Be careful, I don't want, these are not the same numbers. Okay. Now I'm going to do two rewrites. The first rewrite we saw in our last class. What does a remainder of R really mean? It means I have to take Q of X and then I have to add on a fraction of R over X minus lowercase r to get this. That's what a remainder means in this scenario. That if I take this polynomial plus remainder over x minus r, algebraically that would be the same as this. Now we're going to multiply both sides by x minus r. Well, what happens if I multiply the left-hand side by x minus r? That's going to cancel out the denominator, right? And I'll just be left with my dividend, my original dividend. If I multiply q of x by x minus r, I just get q of x multiply times x minus r. Times. What if I multiply this remainder by x minus r? Well, if I multiply the remainder over x minus r times an x minus r, the x minus r's are going to cancel, and I'll just be left with plus whatever my remainder is. So this is the rewrite of what I have right here. What's going to happen if I plug in my lowercase r into the equation, or I should say, into my polynomial function? Well, P of r then will be equal to the quotient, and we have to plug in r. So plug in r, plug in r. So we plugged in lowercase r for all of our x's. And what you should notice is that this thing becomes a 0. And so if you plug in lowercase r, you get the remainder from division. Okay. This is called the remainder theorem. Some people call various parts of this the remainder theorem. Some people just write, this is the remainder theorem. If you have this, then plugging in lowercase r gives you the remainder. All right. I like putting it all in, all the steps to kind of see what's going on. But that's the basics of the remainder theorem. If you have this type of equation, then when you plug in lowercase r, you get the same thing as the remainder when you divide it by x minus r. Okay. Now, what does this mean also? Well, there's another theorem that's just a consequence of this called the factor theorem. And this says if P of x is a polynomial function, and if you plug in r and get out 0, so in other words, r is a 0 here. Then x minus r is a factor of the polynomial function that we started with. That makes sense why? Basically, this tells you that the remainder is 0. And if the remainder is 0, then you can see P of X is equal to X minus R times some other polynomial. Right? Back in the remainder theorem. Or, yeah, this is probably the best way to see it. If our remainder is 0, then X minus R is a factor of that polynomial. And that's what we use a lot. So at this stage, if we turn back to our example we had before, obviously -2 is not a factor. Or excuse me, X plus 2 is not a factor because -2 was not a 0. Okay. But let's say we want to divide that polynomial by X minus 1. I'll use synthetic division. 1, -2, 0, +1, right? When I write synthetic division, remember when I don't have a X term, I have to put in a space for 0. Put in a space for that X term by using 0. So 1 drops down, 1 times 1 is 1. -2 plus 1 is -1. 1 times -1, -1. Add those two up, you get -1. 1 times -1, -1. So you get 0. Multiplying by 1 each time. Right? And so this means that, and again, you can write this 2 different ways, that if we divide by X minus 1, we get a polynomial with no remainder. Specifically, we get X squared minus X minus 1. Which means this polynomial could have been written as this polynomial, X squared minus X minus 1, multiplied by X minus 1. And that gives me a tool for breaking down a higher degree polynomial into a product of lower degree polynomials. So that's one tool I have of being able to break down these things. That work? So we're going to use that tool in 3-6. And that's where we're headed with this. So we're going to look at complex and rational zeros of polynomial functions. And we're going to try to find our complex zeros, our rational zeros. And we already have essentially two tools. One of the tools we've been using the previous couple of days, and that's factoring. Okay? So factoring is a tool. Also, being able to solve polynomial functions that are quadratics is another tool. Right? So you can solve those in a lot of different ways, but solving quadratics, factoring, those are the two big tools we did previously. And now we have this third tool, which is the factor theorem, which says, if I know you plug in a number and get 0, then I know we're going to get a factor, and then I can use division to figure out what this other polynomial is. All right. And so 3-6, we're just going to keep adding on tools on top of that. But before I get into that, I just want you to remember what a 0 is. If P of X is a polynomial function, or any function really, that doesn't have to be function. A 0 is a number, we'll call it R, just because we've been dealing with lowercase r's over there. Number R, such that when you plug in the number, you get out a 0. And remember, graphically, these are the x values of your x-intercepts. Now you might say, well, why do we keep using the letter R here, lowercase r? These zeros are also sometimes called the roots of the function. And that's where the lowercase r language comes from, right? So sometimes these are also called the roots of the polynomial function. And that's where again, lowercase r comes from that version of the language. So a 0 is the number you plug into the polynomial function, you get 0. Those are the x-intercepts. And if you ever encounter a problem that says, find the roots of this polynomial, it's looking for the roots, which are also the zeros, which are also the x values. That's a lot of different terms for the same thing. So let's do this. Let's go to Desmos. Oops. Let's say I have a function, I'll use f of x equals x to the third minus 5x squared minus 18x plus 72. A lot of big numbers there. But if I say, what are the roots of this function? Or what are the zeros of this function? And I give you this graph, I hope that we can all say, this is, let me put a number in front of this so it doesn't go off so high. Let's say, there we go. Scroll out a little bit. There. Notice if I put a number in front, that didn't change where the zeros were. But anyways, so if I say, what are the zeros of this function? You should be able to look at the graph and say, well, there's 1 at -4. There's 1 at 3. And there's 1 at 6. Okay. By the way, this was a cubic. And we ended up with 3 zeros, right? It was a third power. We ended up with 3 zeros. Okay. Not every third power is going to end up with 3 zeros. Let's say I have g of x is equal to x to the third minus 4x squared plus 9x minus 10. That's a third power. But if you scroll out, you see that it only crosses the x-axis 1 time. So on this one, there's only 1 zero. Graphically. We'll talk later and we'll see there's actually 3 zeros to this polynomial function, just only 1 real zero. Okay, so only 1 real zero. So 1 real zero at x equals 2. That makes sense? So graphically, if we ever have to identify where the zeros are, all we're doing is just seeing where does it cross the x-axis? Where are the x-intercepts? Okay. Most of the time, we're not going to have a nice, pretty graph with all of our perfect zeros in it. Okay. Most of the time, we're going to have to find zeros algebraically. And that's basically what most of 3-6 is. Most of 3-6 is how do we find our zeros algebraically? And so we're going to use some tools. The tools we've already dealt with, like I said, solving quadratics, being able to factor, knowing that when you plug in a certain number and get 0, then x minus that number is a factor of the polynomial. So using the factor theorem. Here's another theorem By the way, I'm using the word theorem. Hopefully people have seen that word before. A theorem is just a statement in mathematics that's been proven to be true. Like you can guarantee, it's guaranteed to be true always. Right? So theorem is just a fancy word for a true statement. All right. Here's another true statement. Every polynomial of degree n can be factored into n linear factors and linear over the complex numbers. So if I'm allowed to use complex numbers, I can always factor into n linear pieces. Now, when I say factor over the complex numbers, remember our factoring, when we were dealing with quadratics, we were factoring over essentially the integers. So if you're willing to use like square roots and complex numbers, then you can always use factoring. But that's very, very difficult sometimes. Okay. Now, when I say n linear factors, some of those linear factors may be repeated. And we've seen this before where we had like an x plus 2 and another x plus 2, or an x plus 5 and another x plus 5, or an x minus 7 and another x minus 7, right? So that's the concept of multiplicities. The number of linear factors that have R as a 0 or that have 0 of R. Maybe that's a better phrase. R as a 0, there's only have 0 of R. It's the multiplicity of R. Is that okay? And multiplicities of R. So let me go here. If I write a function, and this is going to be a polynomial function, and I have, let's say, x times x minus 3 squared times x plus 4 to the 5th power times x minus 7. This is the first. I can say the zeros or the roots are, well, this one would give me x of 0. The next one, let me write it this way, x. The next one would be an x of 3. When I set that equal to 0, I get a 3. The other one would be a negative 4. And the last one would be a positive 7 if I'm going in left to right order. So I have 4 zeros with multiplicity so how many factors have x equals 0 as a 0? There's only one factor, right? Just the x. Multiplicity in that case is 1. Multiplicity of x equals 3 is 2, because there are 2 factors of x equals that result in x equals 3 as a 0. So multiplicity of the root 3 has multiplicity 2. Multiplicity of the negative 4 is 5 because there's 5 copies of that x plus 4 factor. And x equals 7 has multiplicity of 1. Now, if you expanded this out, this would be a really big polynomial. It would be a 9th degree polynomial, all right? So if you multiplied all this out, it'd be degree 9. Notice that when you count the multiplicities up and you add those up, it's 9. Because there are 9 linear factors, remember that's what this theorem said. Polynomials of degree 9 are going to break into 9 linear factors. Here they are. That does not necessarily mean we get 9 zeros. That means we get a certain number of zeros, and if we count their multiplicities, there will be 9 of those, all right? So oftentimes the way we say that is if you count the zeros with multiplicity, it's going to add up to the degree of the polynomial. Okay, because of this. So if you count zeros with multiplicity, it adds up to the degree of the polynomial. I'll just write that as a note. You count the zeros with multiplicity. It adds to the degree. That's poor phrasing, isn't it? Okay, so you're already counting the sum is the degree of polynomial of the root. So I'm just trying to get you to think about how many roots to expect, how many zeros to expect, how many x-intercepts should we expect, all right? And so we're building on some tools onto what we already have. That's kind of the whole thing. Now, so far, most of the zeros that we've looked at are either integer or at least real number zeros. Okay. So what I'm going to do, or what we're going to do, is we're going to start talking about the complex zeros of a polynomial and how they have to occur. It turns out that there's another theorem this is sometimes known as the conjugate pair theorem that says if polynomial function has real coefficients, then any complex zeros occur in conjugate or complex conjugate pairs. So just to remind you of what a complex conjugate pair was, if one of the complex numbers is a plus bi, then the other complex number would be a minus bi. Okay. And the reason this has to happen is because the only way we get back to a real number when we multiply complex numbers is if we have conjugate pairs. And I'm not going to go through the whole proof, but basically what you do is you take x minus a plus bi, so x minus this root, and then x minus this other root, this other zero, and we make them complex conjugates pairs. And what you'll see is that when you multiply this out, you get a quadratic with real coefficients. All your i's drop out. Because when you multiply a plus bi times a minus bi, remember, you get back a real number. So it's because of that multiplication. Again, I'm not going to go through the whole thing, but it's because of that multiplication gives you back a quadratic with real number coefficients that this works. And that's the only way we can get real number coefficients. There's no other complex number. If this is one root, that's got to be another. Okay. Here's another theorem Another tool that we can use. A polynomial with real coefficients can always be what I'm going to phrase as broken down, but what the book says is factored into. Quadratics and linear pieces with real coefficients. So if you start with a polynomial and that polynomial has real coefficients, then you can break it down into linear pieces and quadratic pieces with real coefficients. And that is actually a direct consequence of this. Because if it has real coefficients, then all of the complex numbers occur in conjugate pairs. And when those complex roots, remember it says you can break it down, we said earlier, you can break down any polynomial of degree n into n linear pieces over complex numbers. Well, if all of our complex zeros occur in conjugate pairs, then when you multiply, x minus this complex number times x minus its complex conjugate, what you get is a quadratic with real coefficients. So that's this theorem kind of puts together two of the theorems we've dealt with now. If I have a polynomial, I can factor it into n linear pieces over the complex numbers. If it has real coefficients, those complex zeros are going to occur in conjugate pairs. So if we get a bunch of linear pieces, some of them may be real numbers, others may be complex, but the complex ones occur in conjugate pairs. I can take the conjugate pair root, linear factors, multiply them, and get a quadratic factor with real coefficients. Does that make sense? So if you have real coefficients in your polynomial, we can break that polynomial down. By the way, another consequence of this complex conjugate pairs, if all the complex number roots or all the complex number zeros have to occur in conjugate pairs, and we have an odd powered polynomial, if I have an odd powered polynomial, then I have to have at least one real root, one real zero. So that's another thing. If So consequence if or if P of X polynomial P of X is or has real coefficients. And is degree n, where n is odd. Then there is at least one real zero. By the way, a consequence statement in mathematics is often called a corollary. That's just a fancy word for, oh, this comes right from the thing we just talked about. Corollary. By the way, this one we could have figured out way back in 3.1 or 3.2. If you think about this, if we have a polynomial of odd degree, like an x to the third, for instance, what do I know about the end behavior of something with x to the third? Well, a polynomial of degree 3, I know the end behavior as I move left and right. One side's going to go to positive infinity and one side's going to go to negative infinity. That means at some place it had to cross the x-axis, right? So it has to have a real zero. So without even knowing where it crosses the x-axis, I can look at this x to the third minus 4x squared plus 9x minus 10. I know it's got to cross the x-axis at one spot because I know the end behavior. One side goes down to negative infinity, one side goes to positive infinity. Since the coefficient was positive on x to the third, positive infinity on the right, negative infinity on the left. But if the coefficient was negative, I know it'd have to cross the x-axis at one place, at least. Does that make sense? And if the coefficient was negative, as you move left, you go to positive infinity. As you move right, you go to negative infinity. Okay. So that's how that happens. That's how that feels. Now there's going to be one more major theorem that I'm going to get to in just a moment. But with all of these tools, let's start finding zeros of different polynomials. Now, obviously, if it's already factored for me, like it was over here, the zeros are obvious. So my goal is to factor it and figuring out, what the polynomial is, because once it's factored, the zeros floats. What you plug in here to make each of these pieces zero, right? So That's the idea. So the goal is to factor. Sometimes that's easy, sometimes that's not. So let's take a look at a couple of the ones we actually have looked at some of these, but so let's find the zeros of this function. F of x equals x to the third minus 5x squared minus 18x plus 72. And we're going to be given a fact in this case. The fact that I'm going to be given is that x minus 3 is a factor of my polynomial. So if I know one factor, how do I find the other factors? Remember, I want to break it down into something times something times something times something. By the way, how many factors should I expect? How many linear factors should I expect?
At least 3.
3, right?
Or at most 3.
Yeah, exactly 3, right? Exactly 3 factors. Some of those may be repeating. So I know I'm going to get exactly 3 factors, and some of those may be repeating. So here's what I would do. I would say if I know x minus 3 is a factor, then I know that polynomial can be divided by x minus 3. In other words, I know that x minus 3 minus let me restate that. This whole polynomial is going to be this times a quotient. So I'm going to divide my f of x by x minus 3. So I'm going to turn back to 3, 5, and I'll use synthetic division here to make my life a little bit quicker. By the way, if I don't get remainder 0, something has gone wrong. So 1 drops down. I multiply by 3. I get 3. When I add and get a negative 2. Multiply that by 3. That would become a negative 6. Negative 2 times 3 is negative 6. Negative 18 plus negative 6 is negative 24. Multiply that by 3. And sure enough, you get negative 72, which gives you remainder 0. Now I could write the answer here as a division problem. I could say, well, x to the third minus 5x squared minus 18x plus 72 divided by x minus 3 is equal to x squared minus 2x minus 24 plus remainder 0. I don't have to write remainder 0 if I don't have a remainder. But how I'm going to write it is this. I'm going to say my original f of x, therefore, can be factored into a product of x minus 3 times this quotient, x squared minus 2x minus 24. That's the more beneficial way to write that. Now I have a linear factor and a quadratic. So what I'm going to do in this case is I'm going to say, well, how do I factor a quadratic? Or how do I find the zeros of a quadratic? And that takes me back to finding the zeros of the quadratic stuff that we just did, solving quadratic equations. This particular quadratic can be factored over the integers, I believe. If I do a 4 and a negative 6, those things multiply to give me negative 24 and add to give me negative 2. So my function can be factored into 3 linear pieces. Now remember, zeros are the things that make this true. That's why I wanted to factor, right? Zeros are what makes this true. And so the zeros are x equals 3, x equals negative 4, and x equals 6. Hopefully we can do that in our head. What do you plug into here to make 0? What do you plug into here to make 0? What do you plug in here to make 0? All right, I think we've done enough of that type of thing. To make it work. So this is what I want you guys to work on then. Gotta get my now that we've done that. That's fine. I want you to find the zeros of the following polynomial function. P of x is equal to x to the third minus x squared minus 37x minus 35 given x plus 5 is a factor. Go ahead and try this on your own. Uh-oh. Let people do that. All right, so let me go through this one. First off, we're going to divide our function by x plus 5 so I can factor this out. That means if I'm using synthetic division, my r is -5, 1, -1, -37, -35 are my coefficients. 1 drops down, I multiply it by -5, get a -5, -6 there. When I add -5 times -6 is a +30. That gives me a -7. When I add those two up, -5 times -7 is a +35. And when I add those two up, I get 0. Again, I tend not to write the division statement. What I tend to do is just say, well, this means that my polynomial x can be factored into x plus 5 multiplied times x squared minus 6x minus 7. Now I have a linear piece and a quadratic piece. So I say, well, how do I factor the quadratic? Factors of -7 that add to -6. Well, there's only really a couple of different factoring combinations of -7, either 1 and -7 or -1 and +7 over the integers. So this one does factor nicely. My polynomial factors nicely, and that means if I'm looking for zeros, all I have to do is figure out what number do I plug in x to make each piece be 0. So my zeros are when x is equal to -5, x is equal to -1, and x is equal to 7. Any questions about that process? Now, in these last two problems, the zeros always came out to be really nice values, nice integer values. Let's look at one that doesn't come out so nicely. So this is going to look really, really similar. Let's say we want to find the zeros of, I'll call it g of x this time. Really doesn't matter what you call these things, but they're just a function. Let's do x to the third, excuse me, minus 4x squared plus 9x minus 10. Oh, shoot. Should have wrote it here. Given that x minus 2 is a factor, so we know that x minus 2 is a factor. So we're going to divide our polynomial. And again, I'll use synthetic division because that's just a little bit quicker. In cases when we're dealing with x minus r, we can always do that. So 1 drops down, 2 times 1 is 2. Add those two up, you get a -2. 2 times -2 is -4. Add those two up, you get a +5. 2 times +5 is a +10. Add those two up, you get remainder 0. That tells me x minus 2 was a factor, or 2 was 0. So we're all set there. And it also tells me that my g of x can be rewritten as x minus 2 multiplied times x squared minus 2x plus 5. So I have a linear piece and a quadratic piece. In the previous couple of problems, I would factor that quadratic piece. And if I could do that, in this case, I would as well. But if you look at factors of 5, it's either 1 times 5 or -1 times -5 are my only integer factors of 5. neither of those cases add to a -2. So this is not going to factor over the integers, this quadratic. So how am I going to find my zeros if it doesn't factor over the integers? But remember, a 0 just means I get 0 out of here. So what I normally do is, like in the last one, I say, well, each factor I can set equal to 0. Well, we can do that here as well. And we can set this quadratic to be equal to 0 and simply use solving quadratic equations the things we learned back a couple of sections ago to find the solutions to this equation. This solution is obvious, x equals 2, right? That's the first one. That's the first 0, don't forget about that. On this one, I'd probably use the quadratic formula, opposite of b plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. That gives me 2 plus or minus the square root of -16, I believe, divided by 2. Let me check that out. 4 minus 20, and 4 minus 20, -16. Good. Notice here, the square root of a -16. Square root of 16 is 4. But since there's a negative inside the parentheses, that's 4i divided by 2. We can divide both terms by 2. And here are our 3 zeros. One of them is the x equals 2 because of that linear factor. And then that quadratic factor generates out 2 complex zeros. And since our function originally had real numbers as coefficients, those complex zeros occurred in conjugate pairs. One plus 2i and 1 minus 2i. So those are the 3 zeros of this one. Now, just as a side note, if you remember back, my original theorem said polynomials of degree n can be factored into n linear pieces over the complex numbers. We saw that this one could not be factored over the integers. However, if you were to factor this over the complex numbers, what you would end up with, your x minus 2 would still be there. But what these are telling you is that the other factor would have been x minus 1 plus 2i, that complex number, and x minus 1 minus 2i, that complex number. You follow that? So those are the three linear factors that first initial theorem was talking about. X minus this number, x minus this complex number, x minus this complex number. So that very first theorem that said degree n can be factored into n pieces over the complex numbers, n linear pieces over the complex numbers, that's what it's describing. Everybody okay with that? Good. I'm going to erase that then. Let's do some other problems. I'll do a couple different versions of this. So I'm going to take a fourth degree polynomial. And I'm going to give you 1, 0. Let's talk through this. So I'm given one of the zeros of this polynomial function. And one of the zeros is 3 plus I. You know any other zeros in this polynomial function? Well, it has real coefficients. And we have a complex zero. Therefore, the complex conjugate also has to be another zero, right? I know my complex, if I have real coefficients, then complex zeros have to occur in conjugate pairs. So this implies the complex conjugate is also a zero. So 3 minus I also 0. Okay. Now there are multiple avenues to go and get the other 2 zeros, right? We're hoping that there's 2 more, at least 2 more counting multiplicities. So we're going to go look for those. And there's different ways of doing it. If I have 2 zeros already, I know my polynomial function is going to look like x minus that first zero times x minus this second 0 times some quotient that I don't know yet. Right? Now the question is, how do we find the quotient? There's a couple of different ways to find this quotient. One way would be to divide my original expression by x minus 3 plus I. And then after you get that answer, divide again by another x minus 3 minus I. Do you follow that? But here's what I'm not gonna do it that way. So you could do that, but using complex numbers in synthetic division, you can do, that's perfectly fine to do. You can use complex numbers in synthetic division, but a lot of times you get out complex numbers and it's kind of hard sometimes to multiply. So what I'm going to do is I'm just going to multiply this polynomial together. X times x is x squared. Now, this is kind of tricky. I'm going to do x times minus 3. X times, this is minus a minus I, so this is x times a positive I. Is that okay? So positive I times x. That's what happened when I multiplied the x through. Now I'm going to take and multiply this -3 through. So again, -3 times x, -3 times a -3, -3 times a positive I. Look at that. I'm distributing in my head. Hopefully that's not going to throw everybody off. If it does throw you off, just distribute it first and then write another line. Now let's do this one. This is a negative I. So that's a negative I times x. Negative I times -3 gives me a positive 3i. Negative I times positive I gives me a minus I squared. Is that okay? Now I'm going to combine like terms, and lots of things are going to drop out. I have an x squared. Minus 3x gives me minus 6x. This positive ix is going to cancel with this minus ix. This, one of these should be a positive and negative 3i. See, that's why I should have done that. Minus 3 times I. Minus I. Something's wrong. X times that. Oh, that's a negative. That should have been minus. I knew I was going to make that mistake. See, that's why I probably should have distributed. Probably should have distributed, right? Before I started multiplying. Yeah, something like that was going to happen. But the i's cancel out. The 3i and the minus 3i cancel out. And then my constant numbers, this is a 9. Remember, this I squared is a -1, so negative of -1 is a positive 1. So 9 plus 1 is 10. Everybody okay with that? Again, I multiplied it out so that I could get this. And instead of dividing using synthetic division, I'm going to divide P of X by that quadratic in order to get my quotient. And because I'm not dealing with X minus a number, I have to use long division when I do that. So I say, how do I get X to the fourth? I gotta multiply by an X squared. Multiply that whole thing by X squared, I get X squared minus 6X to the third plus 10X squared. Subtract. X to the fourths are going to cancel out. Minus 2x, that's minus negative 6. So I get a positive 4x to the third minus 12x squared minus 32x plus 120. X squared to 4x to the third means that I need to multiply by positive 4x. So I take that positive 4x and I multiply it by this whole thing. 4x to the third minus 24x squared plus 40x. Subtract all that. I get 12x squared minus 72x plus 120. To go from x squared to 12x squared, I need to multiply by 12. I get 12x squared. 12 times negative 6 is negative 72. I get negative 72x. 12 times 10 is 120. Get remainder 0, right? Which is exactly what I should have gotten. So what am I saying? I am saying that that original polynomial that I started with can be factored into x squared minus 6x plus 10 times the quadratic x squared plus 4x plus 12. Now let's look at factors of 12. That's not good. Now, second part's not going to factor either, is it? Factors of 12 are positive 1, positive 12, positive 2, positive 6, positive 3, positive 4. None of those add to a positive 4. I already have the zeros for this quadratic, right? 3 plus I, 3 minus I. So I guess the only thing I really need to do is get the zeros for the other quadratic. All right, in other words, I already know that if I set 0 equals x squared minus 6x plus 10, then that yields 3 plus I and x equals 3 minus I. So I already know that from my work earlier. So now let's set x squared plus 4x plus 12 equal to 0. And then we do our thing. Opposite of b, plus or minus the square root of b squared minus 4 times a times c, all divided by 2 times a. So that gives me -4 plus or minus square root. I don't know what that is, but I know it's going to be complex. I got -32. -32, not only is that a complex number, but it's also one that does not have a perfect square. You could, if you wanted to, 32 is like 16 times 2. So you can break it up. Hopefully everybody understands what I'm doing. -32. I'm thinking of as I times the square root of 16 times the square root of 2, right? I times the square root of 16 times the square root of 2. So that's 4i and a root 2. -4 divided by 2 is -2. 4i divided by 2 is 2i. That's 4 different zeros, and each one is uglier than the next, right? 3 plus I. Three minus I. -2 plus 2i root 2. -2 minus 2i root 2. All right. So what are we saying? We're saying some problems can get fairly messy, right? Some problems can get fairly messy, but it all comes down to, we start with a polynomial and we try to break it down using what we know. And what do we know? Well, we have all those tools. We know how to divide by x minus r. We know how to solve quadratics. So if we have quadratics, we can solve those. We know how to divide using long division. And so if you have 1, 0, we know that if polynomials have real coefficients, complex zeros occur in conjugates, pairs. So all of those things we can kind of put together and use. And this example in particular, put together and used a lot of tools. Now, let me do one other that's not quite as difficult. And then we'll move on to the last theorem we use. I've done a lot more examples this time than I usually do, so we're taking our time here. Let's say I have x to the third minus 5x squared plus 36x minus 180, and I know 6i is a 0. Okay. By the way, what's the conjugate pair of 6i? Well, it's like 0 plus 6i, right? So the complex conjugate pair would be 0 minus 6i. So the conjugate pair is also a 0. So negative 6i is also a 0. So I know that P of x can be written this way. Right? I am going to rewrite this one because I screwed up on my last one. I should have distributed, and then I messed up on one of the terms. All right, x times x is x squared. X times 6i is 6i times x or whatever. Minus 6i times x is minus 6i times x. Minus 6i times 6i gives me a, oops, I'll write this thing, minus 36i squared. Notice that this polynomial, the plus 6i, the minus 6i times x, both cancel out. I squared is negative 1, so that's going to be a plus 36. I'll just take times quotient. So x squared plus 36 is what I'm going to use with my long division. I need to multiply x times the x squared plus 36 to get my x to the third. And I'll line things nicely. So when I take 36 times x, I'll put it in there, in that column. Those cancel, and I simply have minus 5x squared minus 180. What do I need to multiply by x squared to get negative 5x squared? Negative 5. 5 times 36 is 180, so negative 5 times 36 is negative 180. Subtract, and I better get remainder 0 there, right? Otherwise, I've messed something up in my calculations. And so this means that my polynomial is actually x squared plus 36. I know the zeros of that one, that piece, times the linear component x minus 5. So the zeros in this case come from this breakdown. X squared plus 36 has zeros of 6i and negative 6i. And the x minus 5, the 0 from that is just x equals 5. Now, as a side note, or not side note, I guess this is a thing. In Moodle, it's going to ask for your answers. And it's going to say, order it by a real number first, and then by a complex number. So when it asks for your answers, this is like 5 plus 0i, 0 plus 6i, and 0 plus negative 6i, right? And if I said order in least to, or let's go greatest to smallest. What I'm going to ask you to do is to start out by ordering your real number parts. So your real number parts are 5, 0, 0. And then if there's a tie in your real numbers, then you go to the complex parts and you go highest complex number piece or imaginary coefficient, next highest imaginary coefficient. So this would be order from biggest to smallest using real numbers as the first ordering. And then if there's a tie in your real numbers, you go to the biggest imaginary part, next biggest imaginary part. And just so that we're all on the same page. Any questions about these finding zeros problems so far? Okay. Now, here's the deal. Every single polynomial that I've given you, I said this is a 0, or x minus 5 is a factor, or x plus 2 is a factor in my earlier. X plus 5 was 1, x minus 3, all that stuff. What if we're not given anything? What if I'm just given a polynomial and I'm not given a hint about what's a factor? It turns out there's a theorem for that very scenario. And it's called the rational zeros theorem. Okay. So if P of X is a polynomial with rational coefficients, or we're going to mostly just stick with integer coefficients. So let me just write that, integer coefficients. That'll make more sense. Integer And in particular, we're going to write our integer coefficients as a sub n minus 1, and so on and so forth. A1 to the first plus A0. So if I have this, then any rational roots or rational zeros will be of the form B over C, where B is a factor of A sub 0 and C is a factor of A sub A. So what this tells me is this gives me a place to look for my real zeros, my rational zeros. If I have rational zeros, there's only a few numbers they could be, a finite amount. And that finite amount takes all of the factors of A sub 0, all the factors of just this constant term, and divides it by all the factors of the coefficient. Right? There we go. So let's do an example. Find the zeros or the roots of the following polynomial function. X to the third minus x squared minus 10x minus 8. So here are my options. All of my options are going to be factors of -8 divided by factors of 1. Let's do factors of -8 first. Obviously, 1 is a factor. Also, -1 is a factor. 2 is a factor. Also, -2 is a factor. 4 is a factor. -4 is a factor. 8 is a factor of 8. -8 is a factor of 8. So those are all my factors of -8, excuse me. Also, they'd be all the factors of 8 too, because you can do negative numbers. And all the factors of 1 are either 1 or -1. Now here's another little trick. Here I have positive and -1. Here I have positive and -1. I actually don't need the positives and negatives on both sides. So what I can do is I can basically just take the positives on the bottom and eliminate that one. Because anytime I divide by -1, 1 divided by 1, 1 divided by -1 would have been the same thing as -1 divided by 1. Hopefully that makes sense. So if I list all the positives and negatives on top, I can just list out the positives on the bottom. So here are my options. One, -1, 2, -2, 4, -4, 8, -8. Those are the only options for rational zeros. How am I going to find which ones work and which ones don't and all that good stuff? How am I going to find out if 1 is a 0 to this polynomial function?
You can try plugging it in.
Exactly. I'm just going to plug it in. All right. So I'm going to plug in the number 1, and then I'll plug in the number -1, and then I'll plug in the number 2. And then I'll plug in -2. And then I'll do the same thing over here. All right, so let's plug in 1. 1 cubed minus 1 squared minus 10 times 1 minus 8. That gave me a -18. So 1 is not a 0. All right, let's plug in -1. When I plug in the -1, I did get a 0. Perfect. -1 is a 0. And we all say hooray, and then we move on, right? Now, there are, again, options of what you could do. I knew there was going to be at least one real 0, right? Because real number coefficients and to the third power. So odd power told me I was going to have at least one real 0. If you want, you could stop right here and do the thing we have been doing for a while now and use this fact, use the fact that -1 is 0 to find the quotient. When you divide by x plus 1, you can use synthetic division. So this is kind of like starting at the same spot we had before, right? This is like saying, here's our polynomial. I know 1 0 is -1. Let's find all the zeros. However, sometimes we may say, I might just keep plugging in numbers to see if there happens to be another rational 0. If there's another rational 0 or another couple of rational zeros, they're going to show up on this list. That makes sense? So I'm just going to keep plugging things in to see if there's any more zeros on this list. So I'll plug in 2. And I don't know how this is going to turn out yet. When I plug in 2, I get a negative 24.
And when you put it in, like if you were to do it that way, you flip the sign, right? Because it's the -1 out here.
Say it again.
For up there, you have it x plus 1, right? So
Yeah.
that's just the flipping of the sign.
Exactly. That's x minus r. So minus a -1. That's where I get the plus
Okay. Just wanted to make sure I got that straight.
1. Now this one, it turned out also gave me a 0. And I think that's a little bit easier. Once I found 2 zeros here, that's a little bit easier than trying to do division and then factoring. Now I can just plug things in. Now I know there's 2 rational zeros. Could my third 0 be complex? Nope.
No.
Because you can't, if I have 2 and I only know we're gonna have 3 total, my 2 rational ones, I can't have a lone complex. Complex always has to occur in conjugate pairs. So, in this case, I have 2 rational zeros, so I know one of these other ones is going to show up as a 0 too. All right, so let's keep plugging things in. Plug in a 4. Ooh, 4 gave me another 0. Should I keep plugging things in to look for others?
No.
No, I already have 3, and the most I can have is 3, right? Because this is degree 3. So I know that the zeros of this polynomial function are x equals -1, x equals -2, and x equals 4, each with multiplicity of 1. And you could have, again, stopped when you found the -1 and gone through the problem like we've done before. And sometimes you'll have to. Sometimes you only have 1 0 show up in my options. And then I have to do the same process that we've done before. Okay. Any questions about that? Let's do one more example. I'm very, very example heavy today, so. We might as well keep at it. Let's find the zeros of x to the 3rd plus 2x squared minus 17x plus 6. Again, we have integer coefficients on all of my terms in the polynomial. So I can use this rational zeros theorem, which says all of the options for rational zeros are going to look like b over c, where b is a factor of my constant term. In this case, the constant term is 6. And c is a factor of my leading coefficient, which is 1. I like to use the set notation for this, just to list out all the factors of 6. 1, -1. 2, -2. 3, -3. 6, -6. All the factors of 1 are 1 and -1. To avoid redundancy, I'm only gonna count positives and negatives in the numerator. And so my options are 1, -1, 2, -2, 3, -3, 6, -6. Plug in all those. I plugged in 1 and ended up with a -8. When I plugged in -1, I ended up with a +24. Let's plug in 2. By the way, I'm just using the second enter and then changing all the ones I plugged in to 2s. Hopefully you guys know how to do that on your calculator, just second enter. When I plugged in a 2, I got a -12. It's not looking very promising. When I plugged in a -2, I got a 40. Uh-oh. Let's plug in a 3. Oh, I got a 0 when I plugged in a 3. I'll keep going, but I can tell you right now how this is going to end up. You probably can see the writing on the wall. We got one real 0, or one rational 0 out of this bunch. I think that's what we get. Pretty sure 6 and -6 don't work. Technically, I don't even have to try -6 because if I knew that was a 0, that'd only leave me one non-rational. It's not going to work out that way. So, but I'll be thorough. Okay. What does this mean? Well, it means we have a 0 of x equals 3, which means I can write my polynomial as x minus 3 times some quotient. So let's figure out divide polynomial by x minus 3. Polynomial has coefficients 1, 2, -17, 6. 1 drops down times 3, add goes up, you get 5 times 3, 15, add those up, you get -2 times 3, you get -6. Good. All right. Hey, was it? Dang.
I don't think it was me.
It was me, I don't know. Yeah, my bad. Okay. So we get that polynomial. And we're going to solve 0 equals x minus 3 and 0 equals x squared plus 5x minus 2. That one is just x equals 3. We knew that was going to happen. This is opposite of b plus or minus square root b squared minus 4ac all divided by 2 times a. And you actually get real numbers. But the real number involves the square root of 33. Okay? And that's why it didn't show up as nice factoring here. Remember, this is the rational zeros theorem. This is not the real number zeros theorem. It doesn't mean that a polynomial can't have any more real numbers. It means that this is all the rational options. Okay? So the zeros are x equals 3, x equals -5 plus the square root of 33 over 2, whatever number that happens to be. And -5 minus square root of 33 over 2. Okay. So again, these options are my options for rational zeros, right? Options for rational zeros here. But there could be other real zeros, and there could be other complex zeros. We've seen getting complex zeros already. But as you can see in this example gave me one rational zero, which was 3, and then 2 real number zeros that involved ugly square roots. All right. Now, like I said, I did a lot of examples today, more examples than I usually do. But I wanted to be thorough in having you be able to find zeros. So we have all of these tools now that we can use to find zeros. You just have to put them all together and find those zeros, okay? Homework up to section 3.6 will be due Friday. And then the 3.7 we haven't gotten to, we'll just postpone that till next week, okay? So next week, 3.7 will be due. Other than that, have a good one, all right?
All right.